The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
All right, our next presenter will be James Lafikes from the University of Kansas.
Good morning. Thank you all for being here, and thank you for 222 for sponsoring this session. This is culmination of a research project between both of the concrete material research groups at KU, the cracking and the corrosion groups. So a lot of credit is due for the folks who've gone through both of those groups who have been involved with this as well. The sponsors that have helped us go forward with our research include a number of industry folks under the umbrella of the ACI Foundation, along with the Strategic Development Council. We also have a number of state DOTs, along with FHWA, under the pool fund study there. Today I'll be talking about our research background. We're focusing on settlement cracks over reinforcing bars specifically, tying that into how we've developed a test method to evaluate settlement cracking in our labs, and then transfer that into corrosion testing, presenting some selected results from that, and finally wrapping everything up. Significance of bridge deck cracking from a corrosion standpoint is that those cracks can allow for ingress of corrosive materials and chlorides, which if you have uncoated bars can really compromise your corrosion protection, initiate early corrosion, and accelerate the damage due to corrosion losses and spalling of concrete and so on. And from a cracking and durability standpoint, those cracks can accelerate durability issues such as freeze-thaw. KU has looked at a number of bridge decks, a lot in Kansas and even a number of other states across the country. Here's one that's not necessarily doing very well, but relatively representative of what we see. We see a lot of different variations in crack patterns, longitudinal, transverse, map cracking due to plastic shrinkage. Some of the trends that we see for a majority of our bridges, though, is that our crack widths are vastly below 10 mils. We can have average crack widths on our bridge decks range anywhere from as little as 3 mils all the way up to 7 or 8 mils for the ones that have higher crack densities. Those lengths and widths can vary. You can go from a 3 mil wide crack all the way up to 9 mils within several feet of that, and those lengths can also differ a lot. In terms of cracking, you can have early initiation of those along with early initiation of corrosion, depending on your coating integrity if you have any. Moving back into the corrosion lab, we have a number of specimens that we've looked at. We test those both in cracked and uncracked conditions. The thing to note here is for our cracked concrete, we want to control that variable as best as we can, so we have a fixed crack length and width. So in our case, in KU, we use 12 mil wide fixed length cracks that we put directly over those reinforcing bars with stainless steel shims. And with our conventional ASTM A615 black bars, we see immediate corrosion initiation. And the first question, whether we're looking at this from a corrosion or cracking standpoint, is what effects do these cracks have on the service life of concrete? And finally, getting a little bit more narrowed down of what we're looking at with this particular project is, does this stainless steel shim really accurately model cracking in concrete? And if we're out there on a bridge deck survey trying to evaluate the cracking performance of a deck, it's intuitively, yes, if you can look outside of outside your car window and see cracks from there, that's pretty bad. But how bad is it really if you have to get all the way down on your hands and knees with a magnifying glass to see a 1 mil or even a narrower crack there? So can we ignore those small cracks? Or even on a more philosophical level, when is a crack really a crack? So a little bit of background research on that. Rodriguez and Houghton a while ago looked at chloride ingress in cylindrical specimens there. So they split some of those and varied the crack width between 3 and 27 mils. And the main takeaway from that is after they measured chloride ingress through those specimens, they saw that regardless of that crack width or roughness, they saw similar chloride concentrations in those. Counter argument to what we're looking at from a chloride or a corrosion standpoint is that a lot of these cracks tend to not taper with those experimental setups, whereas if you look at it from a bridge deck standpoint, those do tend to taper. You have a wider crack at the surface, and that may narrow down or even close up just below the surface of that concrete. So if you have 3 inches of bar cover, you may not have to worry too much about that, but that's kind of hard to quantify or actually observe if you're standing on that bridge deck. And also, we don't necessarily see early initiation of corrosion, even with high degrees of cracking. A number of culprits that we're dealing with in cracking. We're focusing again on settlement cracking today as our early age cracking. There's also plastic shrinkage due to rapid evaporation. If we're dealing with low water cement ratios, we have autogenous shrinkage. If you're casting hot concrete on top of cold girders or vice versa, you may have to deal with thermal effects. If you have a big drying gradient, that can induce tensile stresses in the top of your concrete sections there, and at early ages that can cause cracking. Then later on in the service life, you have to deal with loading, and hopefully we don't have to deal with this too much because it's kind of difficult to control. Hate it when those people come by and put shims in our concrete forms. So settlement cracking. Mechanism for that, if we visualize just a section of concrete there with our reinforcing bar in the middle, those rebars are in there as kind of a restraint. And when we pour fresh concrete over the top of that, that concrete's going to want to flow over the surface of that rebar. The solids in there, aggregates, are going to want to subside to the bottom, and the water and cement paste is going to want to rise to the top. And in more extreme cases, for what causes those cracks is you can have localized tensile stresses shortly after that concrete begins to set and harden and leave you with a settlement crack. So this figure is also a good example of how you can have a wider crack at the surface of that concrete. It can protrude down, but maybe not necessarily to the level of that reinforcing bar. So to evaluate settlement cracking, we developed a qualitative way of looking at different crack reduction technologies. So we use a 12-inch by 12-inch square by 8 inches deep. We cast concrete over a number 6 reinforcing bar. And for what we're looking at in this particular test program, we used 1 inch of bar cover for the settlement cracking specimens as well as our reference corrosion test specimens. We hold a pretty strict curing and finishing regime with these to make sure that that variable is not controlling anything from one set to another. If you're looking at settlement cracking by itself, here's a diagram of one of our test specimens. All you really need is that top number 6 bar in our forms. So that'll give you the data you need after you pour the concrete over that, allow it to set, and then you can measure the crack length and width over it. It's pretty easy to turn this into a corrosion test specimen. All we really needed to do was provide a bottom mat of steel to serve as our cathode, and then we attached a foam dam around the edge of the top there to hold our salt solution on top. And we use a 15% salt solution with our test program. Here's an example of the end product from the settlement cracking test. So after that concrete cures sets in 24 hours after casting, we measure both the length and the width of those cracks. And for reference, this is what we look at in the corrosion lab for those corrosion test specimens. These are our bench scale specimens. The one on the left is modeling uncracked concrete. This is what we call our southern exposure beam. The one on the right is our cracked beam. Those are cast with a 6-inch long, 12 mil wide stainless steel shim that goes all the way to the surface of that reinforcing bar. It's also important to note that we cast these upside down and flip them over before we start testing. That's so we don't have to deal with or have to worry about settlement cracking or plastic shrinkage cracking. concrete properties that we used for this test program include a water-cement ratio of 0.45. We cast concrete when we get an air content between 6.5% and 9.5%. We used a total binder and water content of 27% paste volume. So for our 100% Portland cement mix, that equates to 593 pounds of cement and 267 pounds of water. Holding that same paste content, our next variable we looked at is doing a 30% replacement with slag by volume, and the third set is doing that 30% slag along with 7 pounds of internal curing water per 100 pounds of cementitious materials via a pre-wetted fine lightweight aggregate. So getting back into our finishing and curing procedures there, when we cast our settlement cracking specimens, we place a slanted, elevated piece of plexiglass plate over the top of those and then seal that with a sheet of plastic over the top to make sure that we're not losing any moisture there or creating any other threats from plastic shrinkage cracking and isolating settlement cracking by itself. And we're leaving that surface undisturbed at the same time. So 24 hours after casting, we record the crack length and width directly over the rebar. And for our corrosion testing, we wet cure for another 2 days. And for a total of 28 days after casting, that's when everything is connected across a 10 ohm resistor, switch is turned on, and the specimens are ponded with our salt solution to begin corrosion testing. And our test for corrosion behavior involve 2 cycles, 12 weeks each, of the first of which being wetting and drying. So they'll be ponded with our salt solution. We take our electrical readings. Those are then vacuumed and dried off underneath heat temps at 100 degrees Fahrenheit. And then the other 12-week cycle is just composed of continuous ponding. So getting into results now, we'll quantify some of our settlement cracking results here, and then get into our corrosion initiation times along with our average corrosion rates based on loss at a fixed time interval. So for settlement cracking, what we've seen in general at KU, our little 10-cent explanation to that, is when we use a crack reduction or shrinkage reduction technology, we're also seeing reductions in settlement cracking. So we'll start with the top. With our 100% Portland cement mixes for settlement cracking, we have a range of 2 to 4 mil wide cracks, average around 3 mils. Crack lengths between 2.17 and around 10.5 inches, average length of 7.5 inches over total of 12 inches of that bar. We see a significant decrease when we use slag and internal curing, with that average crack length dropping quite a bit and even that width dropping from 3 mils down to 2 mils. And just for reference there at the bottom, we have our cracked beams, again, which is just our 12 mil wide stainless steel shim, 6 inches long. So getting into some settlement cracking examples here. On the left, we have our 100% Portland cement mix. One of the more extreme cases there, that has over 9 inches of cracking and a resultant intensity of 0.755. And the one on the right is one of our better performing 30% slag plus internal curing mixes that had only a 1 mil wide, or maximum 1 mil wide crack and a very low crack length. However, the story kind of changes when we get into our discussion of corrosion initiation time. When we take our readings, we say that the corrosion initiates when the rate exceeds 0.3 micrometers per year. So it makes sense that our cracked beam specimens, that series in red, all of those initiated immediately at week 1, and we're using just black bar in all of these specimens here. The thing that isn't necessarily intuitive, though, is that when we use slag with or without internal curing, every single one of those specimens initiated at week 1. Moving right along, when we looked at our settlement cracking specimens with 100% Portland cement, we had to wait till about week 2, and then we only saw about 42% or so of those initiate corrosion. And then we kind of start trickling off there until we get into 12 weeks, which tends to be the earliest time for our uncracked specimens to initiate corrosion. And then some of those can take as much as 20 weeks or even longer. And it's important to note that even though some of those settlement cracking specimens at 100% Portland cement had cracks, not all of those initiated even at 20 weeks. And now getting into a discussion of corrosion rate. This is the average between corrosion initiation at the end and the end of 20 weeks. So for our crack beam specimens, we have the highest average rate. That kind of makes sense. Wide cracks, direct access for chlorides on that reinforcing bar. See an average of about 12 or 13 micrometers per year of corrosion rate there. And our lowest one, of course, is going to be with our uncracked condition. And only slightly higher than that is the settlement cracking specimens with 100% Portland cement. And kind of like how we saw early initiation with slag, with or without internal curing, the average rates for those were about double than that of just 100% Portland cement alone. More on that in a minute. So starting to summarize here, we've seen that even with really narrow, even down to 1 mil wide cracks for some of these specimens, we can see early corrosion initiation with our test series. And for this test setup, looking at settlement cracking, we're concluding that the steel shim or stainless steel shims that we use don't necessarily accurately model these types of cracks. We see a wide range of behavior with our test results. Again, noting that we had about a quarter of our settlement cracking specimens with 100% Portland cement, still not initiated corrosion over 20 weeks into testing. And again, all of our specimens with slag or slag and internal curing initiated at week 1. And as was stated in the previous one, we believe that's for a similar reason there. Those mixes with SCMs, without giving adequate curing time, tend to not have a very robust pore structure and higher permeability. So issue with that that we're trying to address is increasing the curing time there. So whether you're doing a corrosion test or something along the lines of durability, or even just for curing a bridge deck in the field there, a lot of documents and agencies are out there are suggesting higher curing times for SCMs. So these specimens have been since been cast and have just started testing. So other series will attempt to vary crack widths some more. Really great if we can get some specimens that only have 1 mil wide cracks again, because that's pretty significant there if we can move forward and conclude that even 1 mil wide cracks can initiate early corrosion there. Also, to get a more realistic situation in terms of bar cover, most bridges have 2 or even 3 inches of top cover over those reinforcing bars. So we'll see if we vary the bar cover there if we get different results. And finally, looking at other crack reduction technologies and admixtures. So with that, I'm happy to answer any questions. Thank you.
We do have time for 1 or 2 questions.
Okay, your research is very commendable, but I don't want this group to walk away with the impression that slag is going to necessarily reduce the incidence of settlement cracking. You use 30% slag, which is about the bare minimum that would be recognized by use in the industry. Anything under 30% is nothing. Had you used 50% or 60% slag, recognizing that slag bleeds longer and is a slower bleeder, you may not see the same results. So I just don't want this group to walk away with the impression that simply putting slag into the concrete is going to reduce your incidence of settlement cracking.
Appreciate your comment. Yeah, absolutely. SCMs and crack reduction technologies are by no means a cure-all for all that. You really need to make sure that we're curing these things properly and dealing with these materials appropriately. So appreciate that.
Yeah, I like to say, yeah, also very nice work. A couple of comments. One is, I think all concrete will benefit by a little bit more curing, including your OPC. And did you look at, you only had, I assume you had like 3/4 inch aggregate?
1 inch max size aggregate.
Oh, so you have 1 inch cover, 1 inch max size aggregate.
Oh, sorry, you're correct. Yeah, we do we get rid of the 1 inch rocks.
Yeah, I mean, yeah.
Thank you.
Did you look along the bar to see, along the bar level to see how the chloride distribution varied with time? Because I mean, I know I've seen with 3/4 inch aggregate, 1 inch cover, at the 1-inch level, the chloride is not uniform by any means.
Not for the settlement cracking specimens. On the corrosion, or just a corrosion specimen by itself, when those specimens initiate, we will drill into the side of the specimens at the level of the reinforcing bar and then examine the chloride concentrations at those.
Great. Thank you very much.